very good. Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Vijay Ganesh and Curtis Bright from the University of Waterloo and Windsor, respectively, in Canada, who will tell us about an exciting approach to combining SAT solving, which we've had previous talks about, with computer algebra to very much broaden the class of problems one can solve. So as I always do, I'll offer to look at the chat. So if you have a question and you don't know whether to it's a simple question that you should save, or what the status of it is, by all means put it in the chat, and I'll if it's very simple, answer it or raise the question at the appropriate time. And of course, there'll be a chance for questions and a discussion at the end of the talk. So with that, let's see, I think you're starting, Vijay, and then Curtis will continue. So please begin.
Thank you, Michael. Hello, everybody. My name is Vijay Ganesh. I'm a professor in ECE and computer science at the University of Waterloo. And it's great to be back at Harvard. I used to visit Harvard a lot when I was at MIT. And so today, myself and my ex-student Curtis Bright, we're going to present a new approach to solving problems in combinatorial mathematics. And this new approach is essentially combining SAT solvers and computer algebra systems. So allow me to kind of give you an introduction to what SAT solvers are and why you should care about them. SAT solvers and SMT solvers are a class of computer programs that in recent years have had big impact in various areas of computer science, and more recently in combinatorial mathematics and certain areas of physics. So a one-line summary of what a SAT solver is that it's a computer program that takes as input a formula in Boolean logic, Boolean in conjunctive normal form, and decides whether or not it has a solution. If it decides that it has a solution, it says it's satisfiable and produces the solution. If it decides that it does not have a solution, i.e. it is unsat, it would produce a proof of unsatisfiability. The term SMT, which is a short for satisfiability modular theories, is a similar class of tools, except now aimed at first order theories and first order logic in general. And so the question is, we know that the SAT problem is NP complete. Many SMT theories are NP complete, piecewise complete, or even worse. So why is there such an interest in these kind of automated mathematical tools? And part of the answer is that over the last 20 years, there has been a more than 1000x improvement in the performance of these solvers. So much so that today we are talking about building solver-based programming languages, debuggers, type systems, and more recently, as I mentioned earlier, combinatorial mathematical tools. So here is a very quick summary of how one would use these solvers in a context that is distinct from combinatorial mathematics, but which was the inspiration for me to then apply it in the context of combinatorial mathematics. So imagine that you want to reason about a computer program, you're given a specification of its behavior in logic, and how would you go about doing that? So one way to do that is to take the computer program and convert it into a mathematical formula. You're already given the specification in the mathematical formula. You take the conjunction of the two, you give it to a solver. If the solver produces, say, SAT, that means that you have come up with some test cases to test the program against the specification. If the solver says unsat, that means that the program is correct with respect to the specification, because we essentially negate the specification. So I was given this model, my familiarity with this field, because I cut my teeth in formal methods. So as a formal method is, I was thinking, can I lift this idea to other contexts? Can I lift this idea, for example, to mathematics? And the connection can be made in many different ways. One way to think about it is the Curry-Howard isomorphism, which talks about programs as proofs. So if I can find bugs in programs, can I also find bugs correspondingly in conjectures? Bugs here would be correspond to counterexamples. So how would I go about doing that? And so as I researched this question, we try to apply SAT solvers to math conjectures and quickly realized while solvers have are great search engines, they can very quickly search large combinatorial spaces. The problem is that solvers lack domain-specific knowledge, and this really hampers their ability to be effective or as effective as we would like to be in the context of math. So how do we compensate for this weakness? Well, fortunately, we have computer algebra systems, which are huge repositories of domain-specific knowledge about many areas of mathematics, but unfortunately, they lack the search capabilities of SAT solvers. So to me, it was a very obvious thing to combine SAT and computer algebra systems and compensate for their weakness, do something that each of them cannot do by themselves. And with that in mind, we built this SAT plus CAS tool, a math check, using which we have managed to solve many open problems, and my student Curtis will talk about some of them soon. But in order to better understand this, it's important to understand how a modern SAT solver works, at least at a very abstract level, so that the big takeaway from this talk is that you also will be able to use solvers or combination of SAT solvers and computer algebra systems to solve problems that otherwise might be too difficult to solve. So therefore, I have a couple of slides on the background on what a SAT solver is. So allow me to start with the basic definitions of the Boolean satisfiability problem. So the problem is given Boolean formulas in conjunctive normal form. So conjunctions of disjunctions of literals decide whether they are satisfiable, right? And we know that this problem is NP complete, believed to be intractable. But of course, the big surprise, which kind of separates practice from theory today, is that SAT solvers are able to solve formulas with millions of variables and clauses in them. And that's another area of research that I'm focused on, is how can we bridge that gap between theory and practice? How can we build new complexity theoretic tools to better understand this phenomenon? So with that out of the way, allow me to now describe to you at a very high level what a modern SAT solver looks like. A modern SAT solver, whenever we use the term SAT, we typically mean this kind of solver, which is called a conflict-driven clause learning SAT solver. So here is how it works. It takes as input a Boolean formula, we colloquially refer to as a SAT instance, and it performs propagation. What do we mean by propagation? Imagine that you have a clause which has exactly one literal in it, let's say X. That means that if you care to decide the satisfiability of the formula, then you have no choice but to set X to true and simplify the formula with respect to that. You keep doing that, and the BCP, this is also called Boolean constraint propagator, and this particular method can produce one of three results. It could say either the formula is SAT, it could say the formula is unsat under the current partial assignment, or it could say unknown, that it doesn't know what to do next. So the next step is it's checking whether the formula is indeed unsat under the current partial assignment. That's called conflict. If the formula is unsat under the current partial assignment, unsatisfiable under the current partial assignment. And if it is not unsat under the current partial assignment, it goes to the left side of your screen and it checks whether all the variables have been assigned. If so, we know that the formula is satisfiable and the tool will return SAT. Else, it will choose a variable using some heuristic, add it to the queue of unit literals, and then simplify the formula in a loop. It continues to do that until such time it gets into a conflict, at which point in time it performs conflict analysis. The idea behind conflict analysis is essentially a form of root cause analysis. Why is the formula unsatisfying under the current partial assignment? What is the root cause? For example, you could have a formula with 1 billion variables in it, and this is not out of the question, this actually happens. And it could be that 3 variables were responsible for that formula being unsatisfying under the partial assignment, which may have millions of variables in it. So the conflict analysis job is to discover those 3 variables and tell the tool, tell BCP, never again to explore that part of the search space. And so it adds a fact, which is implied by the input formula, to the set of facts that it knows about the formula, and says, never again you are to visit this part of the formula. And in this way, it is able to prune away large parts of the search space, shrink the search space, and thus scale to very large combinatorial spaces. So another view of this is you can think of conflict-driven clause learning SAT solvers as a reinforcement learning engine with deductive feedback loop. So you have an agent, which is the decision heuristic that is making decisions. And when the partial assignment is unsatisfying, it asks the environment or the teacher, the agent can be a student and the environment is a teacher. Why is it that this particular partial assignment is not satisfying for my input formula? And the clause learning system, which is the teacher here, will analyze and say, here is the true reason as to why this particular partial assignment is not satisfying. Learn this clause and avoid this part of the search space. This loop continues until you converge to the correct answer. So now the question was, how do we adapt this to the setting of combinatorial mathematics? This model works great for finding bugs in software and hardware systems. How do we modify this for the setting of combinatorial mathematics? So that's where I came up with this idea of SAT plus CAS. And with my students, we were able to solve many problems and build this tool, MathCheck, and its successors. So here is the same idea that I mentioned a few minutes ago of how do you test code, but now how do you test a mathematical conjecture? You give the mathematical conjecture to your an analysis tool that will somehow Booleanize this conjecture, finitize the space that has to be checked, give it as a logic formula to the SAT plus CAS tool. But now, in addition to just feeding the logic formula, you also give domain knowledge, and the computer algebra system would then help the SAT solver to prune the search space more effectively than otherwise. And if the solver says SAT, typically that would correspond to a counterexample. And if it says unsat, that would say at least the part of the space that I checked does not have any counterexamples. So here is the same picture of a SAT solver, except now augmented with a computer algebra system. So observe that I have added a computer algebra system both to the BCP, the Boolean constraint propagator, and the conflict analysis. And here is one way to think about this. So imagine that I am making decisions in my Boolean search tree, and I do propagation. So as soon as any literal becomes unit, I propagate, simplify the formula. But I could also query the computer algebra system and ask, are there implications of this particular assignment that I'm missing? And the computer algebra system might come back with its domain knowledge and say, yep, here are the implications that you're missing. Go and check these. That is how it would be used in the context of propagation. In the context of conflict analysis, what happens is that you might have a partial assignment, which is you do not yet, may not know yet that it is completely conflicting. So this image is a little bit imprecise. So here what will happen is that you would query the computer algebra system as, is it possible that this might lead to a conflict? And this enhanced conflict analysis method will actually say, yep, this is potentially leading to a conflict. Do not even go down this path. Stop right here, go back and search in a different way. So this is how we enhance the SAT plus CAS tool. And again, going back to this analogy of thinking about the CDCL solver, but now with this enhanced CAS capability as a loop between a student and a teacher, and both aspects are enhanced with the CAS system. And this would allow you to search combinatorial spaces that otherwise might be too hard for the SAT solver alone. So we published this for the first time as a paper in the CADE conference, the MathCheck tool, using which we were able to settle a few open graph theoretic questions. And then working with Curtis and others, we were able to extend this to many other domains. So with that introduction, I would now give it over to Curtis to explain how he further enhanced the MathCheck tool and applied it to various combinatorial problems. Thank you. So I'll stop now and I'll let Curtis take over. Curtis, please go ahead.
Okay. All right. Thank you, Vijay, so much for the nice introduction to SAT plus CAS. So, and thanks, Michael, for the invite. This has been a really interesting seminar series. So, as Vijay mentioned, MathCheck was the first SAT plus CAS system, and I worked since around 2016 in extending it to many different areas, but I'm going to talk about two in this talk. The first one being we used MathCheck to search for large Williamson matrices, and the second one we used MathCheck to produce certificates of for Lamb's problem in finite geometry. This was kind of a high-profile problem, and we ended up winning a Best Paper award. So we're happy that people are taking notice of these new sort of systems. So first, let's start with the Williamson conjecture. So this is a conjecture which deals with this concept of a Hadamard matrix. from combinatorics. So they're really easy to define. We're going to have a square matrix. The entries are all going to be either 1 or -1. And if you take any two rows of this matrix, the rows are going to be orthogonal to each other. So equivalently, you can say, if you look at the two rows, half of the entries are they're going to match in half the entries, and they're going to disagree in half the entries, right? This will make their inner product 0. And so any two rows are going to be mutually orthogonal. And this is quite a restrictive condition. It's very difficult to find Hadamard matrices of a given order in general. In fact, it's an open question for which orders these matrices even exist in. And this is despite being very well studied for over 100 years. Hadamard was looking at them, in 1893, and it turns out they have lots of applications to science, engineering, statistics. And this is one really nice one. I love this photo. This is from a NASA press release in the 1960s, and here you see three scientists, very proudly standing next to a framed copy of a Hadamard matrix that they found. This was the first known Hadamard matrix of order 92. And they were interested because they were wanting to communicate with spacecraft, and Hadamard matrices are useful for constructing error-correcting codes. And you can actually see over my shoulder, I have a cross-stitched framed copy of a Hadamard matrix that we found using MathCheck, as I will describe, designed by my partner. And the construction that we used is based on Williamson's construction. So Williamson was a mathematician who in 1944 wrote this amazing paper where he gave a construction to generate large Hadamard matrices. So he wasn't able to prove a general theorem, but he was able to find a lot of explicit small examples. Well, relatively large examples for the time, but small compared to some of the ones we know today. So here is one of the small examples he gave. This is an order 8 by 8 Hadamard matrix, and it's constructed using 2 by 2 Williamson matrices, as I'll describe. So the colors kind of denote the structure in this matrix. And so then what is a Williamson matrix? The general idea is we're going to not search for the full Hadamard matrix, but we're going to search for the small submatrices. We'll call them a quadruple of Williamson matrices, A, B, C, D. They're going to have plus or minus 1 entries. But the interesting property that they have to satisfy is that the sum of the squares of those quadruple of matrices should give you basically the identity matrix up to some scaling factor. In particular, all the off-diagonal entries of the sum of squares they all have to be 0. Okay, so if these matrices have some symmetry properties, if they're symmetric, and for simplicity, we'll just say they're circulant, meaning every row is a cyclic shift to the previous row, then they're going to be called to be a set of Williamson matrices. And so one simple example is shown at the bottom here. These are quadruple of Williamson matrices of order 5. Okay, you can see the circulant property. It makes this nice diagonal looking pattern. So Williamson in his paper never actually conjectured this, but this kind of became known as a folklore conjecture, that Williamson matrices should exist in any order. Because when scientists who wanted to construct large Hadamard matrices went looking for these Williamson matrices, they seemed to always exist in all the orders that they could find, but they weren't able to prove any general theorems. And Williamson even notes this in his original paper. I have a quote from it down here. He basically says it would be really nice to prove some kind of a general theorem, right? He was only able to show the existence of Williamson matrices for some small orders. So in particular, he examined the powers of 2. He was able to find Williamson matrices in orders that were powers of 2 up to 2 to the 5, which is 32. And I've colorized the matrices that he gave in his original paper. So this is from 1944. And actually, it's quite impressive that he was able to construct Williamson matrices of order 32, because remember, he's all by hand, right? Computers weren't around back then. And these matrices are, the search space for matrices of order 32 is just astronomical, right? So he doesn't actually say exactly how he was able to construct them, but you can kind of guess based on the results in his paper. He proved a bunch of nice results about Williamson matrices, and then was able to, with some kind of trial and error process likely, come up with some examples which happen to work, right? And so he gives it in his paper. Here are some examples. I'm not able to prove a general theorem, but they at least exist up to, all powers of 2 up to 2 to the 5. So when I first see it, this image here, the thing I think about is, well, does this pattern continue? Can you come up with Williamson matrices in all powers of 2? And surprisingly, even the next open case, which would be 64 by 64, that was even open when we started working on the problem. It was not known if Williamson matrices existed even in order 64. So what we did then was, as I will describe, we used MathCheck to run searches for Williamson matrices. And we searched all the even orders up to 70. So that included 64. And lo and behold, they do exist in order 64. And not only did we find just one quadruple of Williamson matrices of order 64, we actually found thousands of them. It turned out there was just a plethora of Williamson matrices of this order. And so then once you have that data at your fingertips, you can start to analyze it. Right? You can start to look for patterns now that you have all the Williamson matrices of order 64. And indeed, we were able to find a pattern which generalizes to all powers of 2. So now I'm happy to report we have this general theorem. After 75 years, we've kind of finished, or at least in the powers of 2, we've answered Williamson's question of, do these matrices always exist? And they do exist in all powers of 2. And so we were able to do this because now we have the computational engine, which has allowed us to get that data, right? If Williamson had access to that data, perhaps he would have been able to prove that general theorem. But when you don't have the data at your hands, it's hard to know what patterns to prove, right? So we were, for the rest of the talk, I want to basically describe how we were able to run this search. So we weren't the first people to search for Williamson matrices, of course. I'll focus on the even orders here. The sort of state of the art in 2006, which was using a computer algebra system, was getting Williamson matrices up to order 22. And when we came along, we came up with a SAT approach, as I'll describe, and it ran okay. It ran up to order 30. All right, so it was better than the computer algebra approach, of course, though it was 10 years later. But this should kind of raise some eyebrows, because remember, I said with MathCheck, we were able to search up to order 70, right? And so this is not just some kind of slight improvement. This is an astronomical improvement, because remember, the search space for Williamson matrices is growing exponentially. Even increasing the order by 1 or 2 is significantly increasing the search space. So going from order 30 to order 70 represents an increase in the search space of 25 orders of magnitude. So it is just astronomically larger. If you had told me when I started working on this project we would search order 70, I would have said, you're crazy. This is totally infeasible. It's just too large. And yet we did this search exhaustively. And so my goal for the rest of the talk is to give you an intuition of how this could even be feasible, right, to run such a large search. Okay, so first we have to encode the problem into SAT. If we're going to use a SAT plus CAS approach, first we need a SAT, a Boolean formula, which is going to represent the existence of Williamson matrices of a given order. And so the nice thing about Williamson matrices is that all of the entries are either 1 or -1. And in Boolean logic, all of the variables are either true or false. So you have this nice correspondence. We can define a variable for every entry in our matrix. The variable, if it's true, that's going to denote an entry of 1. And if the variable is false, that's going to denote an entry of -1. In fact, since you have this symmetry properties in our matrices, you only need the variables in the first row because they're going to define the entire matrix, because every row is a cyclic shift of the previous row. So this is just a one matrix example for matrix A. You can do the same thing for B, C, D, and you come up with a bunch of variables which are going to define matrices. But then you want to specify that those matrices are, in fact, Williamson. You want to do this in Boolean logic. And in fact, there's a simple way to do this. So recall, you want to specify that all the off-diagonal entries in this sum of the squares are going to be 0. What you can do is for every off-diagonal entry, you can specify an arithmetic circuit which is going to compute that entry, in terms of the Boolean variables. And that circuit then can be converted into conjunctive normal form, which is just the standard format of what SAT solvers take as input. So I won't go into the details of how you can, construct those circuits and how you can convert to the conjunctive nominal form. This is all really standard material for people who work in SAT. That's not the new thing here, right? So you can put together a SAT encoding which is going to specify that Williamson matrices of order n exist once you fix n, and then you can feed that to a SAT solver, and the SAT solver can then look for Williamson matrices. So it's either going to find an explicit satisfying assignment, which would then give you an explicit set of Williamson matrices, or it's going to say, unsat, there are no satisfying assignments with a certificate, and that will then constitute a counterexample of Williamson's conjecture. It would prove that Williamson matrices of a given order n don't exist. So this is what we did, and we got up to order 30. So it worked relatively well, but there was a problem, as Vijay mentioned, right? The problem is the SAT solver has no knowledge about Williamson matrices. It's really, all it sees is just trues and falses. And there's lots of facts that mathematicians have proven about Williamson matrices, which are actually quite beneficial, as we'll see. One of the main examples is given on this slide here, and this is known as power spectral density filtering. The idea is as follows. Say we have a Williamson matrix A. If you take its first row, say the vector here is a vector of length n, and you compute the Fourier transform of that vector, the maximum squared magnitude of the Fourier transform is upper bounded by 4n. So this is a linear upper bound in the order of the matrix. This is actually quite a substantial result, because it is almost never going to be satisfied. If you just gave a random matrix plus or one minus matrix A, the PSD, you can give some kind of an argument that heuristically you're expecting this to be quadratic in n. It's very unlikely that it's going to be so small. So this is something telling you something very specific about Williamson matrices, and this is very useful if you could exploit it, right? Because it's going to dramatically reduce the size of the search space. So the problem, though, is how do we specify this in SAT, right? If you want to compute this explicitly, you're going to be evaluating sums which look like this. It's a sum of the entries scaled by, multiplied by some powers of roots of unity. These are complex numbers. So this is, it's not going to be something you're going to express in SAT and have it work out well at all. So we have a problem, right? And this is, if you take one thing away from the talk, this is the idea. If we were going to use the PSD filtering, which is going to be a very powerful method of reducing the search space, we need two things. First, we need a way of computing the PSD values, of course. And secondly, we need a way of avoiding matrices which fail the condition. We only want to look for matrices which pass the PSD test. And this is exactly why SAT plus CAS is so great, because CASs have been designed and engineered very, very effectively to compute things like PSD values, right? There's an algorithm known as the fast Fourier transform. You can use it to compute the PSD values very, very fast. The second thing is SAT solvers, as Vijay described, are extremely good at doing this sort of search with learning process. And so we can specify, once we've hooked up the SAT solver to the CAS, we can specify we want to avoid matrices which fail the PSD condition. And so this is how the setup is going to work. The SAT solver is going to be finding partial assignments which satisfy the formula, right? Some variables are going to be defined true. Some variables are going to be defined false. Some variables will be left undefined. Eventually, you're going to have enough variables defined that they're going to define a matrix. So say the matrix A here. You can pass the matrix A to a CAS, and the CAS can then compute the power spectral density of the matrix. If it's too large, which it almost always will be, it can then tell the SAT solver, don't ever try that matrix again, because I have this theorem, I know that this is never going to be a Williamson matrix, right? And so it blocks a big part of the search space. And this is something the SAT solver itself would never have learned, right? Because it has no knowledge of PSD values. Only the CAS knows about that. So, but the CAS, once the CAS has this information, it can whisper in the SAT solver's ear, okay, block this, and execute the search as you're, keep executing the search, but never try this matrix again. And you can kind of make a heuristic argument that this is going to exponentially decrease the search space. And indeed, in practice, if you look at the running times, it actually exponentially, there's an exponential speed up in the running time if you compare the SAT approach to the SAT plus CAS approach. And so at some point, it really doesn't even make sense to use the SAT solver just by itself. Like I said, we've never been able to scale up to order 70. It would just been totally out of the question if we just had to use the SAT solvers. But using the SAT plus CAS solver allowed us to scale up to order 70.
Could I ask a question?
Yes.
Yeah. When you use the CAS and you compute this norm, does it really have to take the entire matrix and compute a number, or does it take a partial matrix and compute upward and lower bounds? Because I would have guessed, especially for the big matrices, there's a lot of them. And, just doing it one by one, I'm surprised that it would have such an effect.
So it's taking one of the, so just the matrix A, for example, that's only going to be a small part of the full matrix, right? It's because we have a quadruple ABCD, we're just going to focus on matrix A, compute its PSD value, and then block, once A comes back with a PSD too large, you avoid that matrix in the future.
But even, rank 70, it's a 70-dimensional Boolean vector, right? So,
yes.
So really, you're kind of remembering, this matrix couldn't work, this matrix couldn't work, but the number of matrices that you can individually sample is negligible, right, compared to 2 and 70.
Yes, that's a good point. There are more filtering that we used as well. So this is just one of the main ones. But yeah, if you have to, there's if you look at the paper, there's also this concept of compression. So you can compress a order 70 vector to a order 35 vector, and then you can run your search over the 35 vectors. So there's more tricks involved. Yes.
I see. Are you going to tell us the tricks, or they just walk back?
If you look at the paper, they're all lined out in there. I just wanted to get onto another problem rather than going through every number of tricks. But yes, that's a good point. Yeah, so you can't sample all 2 to the 70 matrices A of this form, right? Because there's too many of them. Okay, so just to sum up the results here, we have found over 100,000 new sets of Williamson matrices, which was quite surprising to, well, me at least, and some of the experts in the area, because previously there was around 200 have been previously found by computational means. It turns out in the powers of, if you're searching an order which is divisible by a large power of 2, there turns out to be many more sets of Williamson matrices than, for example, in the odd orders. So this is basically, we kind of realized this by just looking at the data, and was able to, that's how we were able to find so many new sets of Williamson matrices. So it turns out Williamson's conjecture is false. This was known. It was known that order 35 was a counterexample. And so not only did we verify this using MathJack, we also proved that it was the smallest counterexample simply by finding examples in every smaller order. So we know 35 is the smallest. And we've made this new conjecture now that Williamson matrices exist in all even orders. This is still open. It may or may not be true, but we know it's true up to at least order 70. Okay, so that will be the first application. And I want to do one more application, which is Lamb's problem, which is really nice. I like this application because it has a lot of history. It goes, way back to the granddaddy of all mathematicians, Euclid. And we all know Euclid, right? He defined the axioms for geometry. And I think many of us know the story, right? Euclid defined 5 axioms. The first 4 were very simple. The 5th was more complicated. All the axioms were thought to be self-evident or obvious, but the 5th was more complicated. So that's a bit unsettling. They thought, mathematicians for 2,000 years thought, well, let's prove this more complicated axiom in terms of the simpler axioms, right? Like proving a theorem. But now we're basing it on just the simplest possible axioms. They consistently failed to do this for 2,000 years, and it was eventually realized with the work of Gauss and others in the 1800s, that, well, this is just flat out impossible because there are models of geometry that are not going to satisfy Euclid's fifth postulate, this parallel postulate. So examples of this is like the extended Euclidean plane. Let me give you a couple more exotic examples. This is when you have only a finite number of points in your geometry. So on the slide here, I've represented these geometric structures known as finite projective planes. So these satisfy Euclid's axioms, except for his parallel postulate, which will not be satisfied. So they satisfy three simple axioms. The first one is every pair of points define a unique line. This is one of Euclid's axioms. The second is every pair of lines are going to meet at a unique point. And this is basically saying parallel lines don't exist. So this is saying that the parallel postulate does not hold. And then the third one is just saying all the lines contain the same number of points. It's going to be this 1 plus n, where n is defined to be known as the order of the plane. All right, and then I can give you explicit examples in orders 1, 2, and 3. And the great thing about geometry I like is that you can visually represent it, right? So you can actually check. You can go in and say, okay, I'm going to take any 2 points. Yes, they define a unique line. I'm going to take any 2 lines. Yes, they're going to meet in exactly 1 point, right? So you can, it's not easy to find these things when the order gets large is the problem. And in fact, the classification of the finite projective planes is still an open question. We don't know for what orders they exist, but what we do know is that they exist in every order up to 9 except for 6. Now 6 is an interesting case. You can actually just eliminate this case purely by a mathematical theorem. There's a property which cannot possibly be satisfied in the order 6 case. And this property will also eliminate some orders, other orders, but it does not, interestingly, eliminate 10. And so that makes 10 the first unsettled case. For many, many years, 10 was unknown. And this became like a notoriously difficult problem. It was very famous, and no one could find a projective plane of order 10. No one could prove one didn't exist. Eventually, it was resolved, but it was resolved not by a mathematical theorem, but by a computer search. And it became known as Lamb's problem after Clement Lamb, who was a mathematician at Concordia University. And he put together a team of programmers who ran an exhaustive search using a supercomputer in the 1980s. It ran for months, and it came back there. It didn't find one. Okay, so it doesn't exist. Well, it's a bit unsettling because this is not a mathematical proof in the standard sense of the word. In fact, there's no way to check their computations because their code isn't public, and even if their code was public, it's very, very difficult to say prove that this code is bug-free, right? And there could have been a hardware glitch, there could have been an administrative error, and there could have been a bug. And in fact, anyone who's used a computer, even software which is running millions of times every single day, used all over the world, it has plenty of bugs, right? That's just a reality of software. So the fact that you're running a single program one time, it's almost an inevitability that there's a bug there, right? The question is, was it serious enough that it influenced the final result? And this is where we came into the picture. So we wanted to put this on a bit more of a sound foundation. We wanted something which was checkable by a third party. And as Vijay mentioned, SAT solvers produce certificates of unsatisfiability. So this is a perfect fit for a SAT solver, right? And we generated the first set of certificates that a third party can then use to check the result. And so you might be thinking, well, what if SAT solvers themselves are complicated pieces of software? And indeed, yes, SAT solvers do have bugs because almost all programs have bugs. But the insight here is that we're not actually trusting the SAT solver, because the SAT solver produces a certificate which is then checked by a proof verifier, and the proof verifier is a much simpler piece of software than the SAT solver. So yes, you do have to trust the verifier, but that is much, we're not trusting any search procedure here. That's the main takeaway. Okay, so how do we do it? First, you have to come up with a way of reducing your problem to SAT. Now, we're not actually going to use those nice colorful diagrams, right? That's the human way of representing these projected planes. But you can just encode that data, the visual data that I showed you, into a 0-1 matrix, right? So you let the points be represented by columns of this matrix, and you let the lines be represented by rows of this matrix. And so if there's a 1 in the ijth entry, that means that the ith line contains the jth point. Okay, and so the axioms are then going to specify that all the number of ones in every row and column is constant, right? It's going to be 1 greater than the order of the plane. You also specify that there's no quads in the matrix. So a quad is a rectangular submatrix with 1s in the corners, because if there was a quad in your matrix, that would give you 2 lines which meet in 2 points, right? And all lines are going to meet in exactly 1 point. So again, the SAT community has developed a lot of different ways of encoding these sorts of constraints into SAT. That's not the novelty here. You can come up with a SAT instance which encodes the constraints at the top into SAT. The problem is if you give the instance to a SAT solver, it's never going to finish, right? In any reasonable amount of time. The search space is just astronomical. SAT solvers do their best, but they're only so good. And the problem is, LAM could solve this in the 80s. Why can't a SAT solver solve it? Well, it doesn't know the mathematics. And so here is exactly why we had to use the CAS. And one of the primary ways we use the CAS is shown on the slide here. So again, the SAT solver is finding partial solutions. It's assigning some variables to true, some variables to false, and some variables undefined. Eventually, you're going to define a partial projective plane. So something like this. So this has 4 points and 6 lines, and it satisfies the axioms up to those 4 points. So you can give this partial plane to the CAS, and the CAS can analyze it. And in this case, the CAS can notice something. It can compute the set of symmetries of this partial plane. If you so example 1 symmetry would be if you rotate the whole thing 180 degrees, you get something which looks the same actually. So the colors have been all switched around, but it looks structurally the same. This is an isomorphism. And every time you find an isomorphism, you can actually block it. Because think about it, anything which is extendable from the first structure is also going to be extendable from the second structure. So by blocking the second one, you're actually not losing any solutions up to isomorphism, right? Any solution that's in the subspace that is blocked is going to also be in the subspace that you're keeping. So this is powerful because every time you find, the CAS finds an isomorphism or a symmetry, you've blocked more of the search space. And this is part of the search space the SAT solver would otherwise basically have to redo the computations. So this is very useful when there's a lot of symmetry in your search. So to give you a sense of the results in Lamb's problem, you can split up Lamb's problem into 3 cases using some sophisticated coding theory. I won't go into the details there as well, but this was all known back in the 70s and 80s. So each of the cases are more and more difficult. The first case is the simplest. I believe there was about 4 different independent verifications of this case using computer algebra. In the literature, there's a bunch of different papers written on just resolving this case alone. We ran those computer algebra approaches on modern hardware, and they ran from between 3 and 80 minutes. Then we also came up with this SAT encoding, which I described to you. We gave it to it actually ran, just for the case 1, it ran in 5 minutes. So that was actually beating out a lot of the CAS approaches, surprisingly enough, right? We weren't using any CAS in that search, but here's the really cool part. When we hooked up the CAS to the SAT solver, it ran in seconds. So it's something like 0.1 minutes. So it was far and away the fastest way of resolving that case. And then we moved on to cases 2 and 3. So the SAT solver had no hope of solving it because the search was too large. In fact, it was so large, I only know of 1 independent search that was run. It used a computer algebra graph package known as Naughty for graph isomorphism. And it ran in about 40,000 hours on modern hardware. So quite quite a lot of computing time, and we resolved the second case in only 30 hours. So it turned out there was lots of potential speed up there based on the symmetries. And then the third case, it ran in 16,000 hours. It turned out this case, the main part of the search didn't have much symmetry. So we kind of had to reduce back down to just a pure set approach. But even still, we have the certificates there was the main novelty. So not only was it faster, it was also more certifiable. And so that certifiable, I keep stressing, but this is actually not just me being pedantic. This is actually quite an important point. You really do want a certifiable search when you have untrusted search code, right? Because I know from experience, it's just too easy to, despite your best efforts, it's very easy to introduce a bug when you're trying to optimize search code. And indeed, we found discrepancies. So there was an independent verification of Lamb's search from about a decade ago that found discrepancies in Lamb's result. And we found discrepancies on top of the discrepancies, right? It just goes to show how difficult this all is to get exactly right. But so what I mean by discrepancy, they published some partial results. So all of the searches found no projective plane of order 10, but when you're finding partial projective planes as you're doing the search, they publish some partial results, and then we found discrepancies with that. So one of them is the discrepancies is shown on the right. This is a partial projective plane of order 10. It has 51 columns. The full plane would have 111 columns. So this is easy to check that it's a partial projective plane. It has no quads, and every column is the same number of ones. So it's obvious that it satisfies the axioms up to that point. But the independent verification was predicated on the fact that this plane didn't exist. This is what they asserted in their verification, and it turns out it does exist. So, if this partial matrix had been extended to a full projective plane, it would have been missed by the previous search. So this just goes to show you this is actually quite important to get those certifiable resuls.
Could I ask
Yes.
questions? Yeah, the one is from the chat, Stanislav Renjowski. He just asked, is there a simple explanation of what the cases 1, 2, and 3 are?
Yes, so I don't know if I want to go into, basically it's based on the existence of, you look at the linear span of the vectors of the projective plane over the finite field with 2 elements, right? And then you can prove that there has to be a vector of weight 15, 16, or 19, where the weight of a vector is the number of ones in it. All right, so case 1 is saying there has to be a vector of weight 15 in that, if you look at that code, and case 2 is a vector of weight 16, and case 3 is a vector of weight 19.
Okay, well, that's pretty simple. My question, so I know something about how you would get a certificate out of a SAT solver, but how do you get a certificate with the SAT plus CAS? So like if I'm telling it ignore things that are related by an automorphism, how would I put that into my certificate?
Yes, this is an excellent question. This is one of the things that we struggled with. So in general, a CAS is not going to produce any certificate of its result. You have to trust the CAS. But in this case, we used a CAS, this library known as Naughty, which tests for graph isomorphism, right? So it's going to say this is isomorphic to this. So in that case, it actually produces a certificate because it produces a labeling of saying that this graph is the same as this graph, and it gives you the permutation of the nodes, which then you can check, yes, these two things are going to be isomorphic. So there's it's kind of a 2-stage verification. First, you have the pure SAT verification, but at some points in that proof, we have this CAS learned fact, which says, okay, this is isomorphic to this. And so then we go to we check the Naughty certificate, right? So we have an extra checker, which then checks every time we've blocked part of the search space, yes, it actually is isomorphic to a part which was kept.
Very nice, thanks. Yeah.
Yes, thank you. Yeah, that's an excellent point. Okay, so just I won't have time to go through all the different results that we use MathCheck on, but this is kind of a summary. It's actually quite interesting to look at the variety of CAS functionality. And that's one of the benefits of the CAS, is that you're just kind of spoiled for choice. There's so many different functions in the CAS. So there's a lot of flexibility in how you use the method. So the Fourier transform, of course, comes up in many of these problems. Graph isomorphism, as I mentioned. We also used nonlinear optimization. We used traveling salesman solving and shortest path solving for graph theory problems. If you are interested, check out the website. All of these problems have been specified, and we published many papers on these topics where it's all spelled out in detail. All right, so I just want to sum up with a conclusion. I want to stress how many mathematical problems this sort of paradigm is potentially very effective at, right? Anytime you want to run a mathematical search and you want fast verifiability and expressiveness, then I would highly recommend you look into SAT plus CAS methods, because the SAT solver is both fast and verifiable, and then the CAS is very expressive, right? So you can use both of the tools in the way they're meant to be used. You don't want to reinvent the wheel. You could always write your own search, right, for some mathematical object, but unless you really know something about the space, you're probably not going to beat a SAT solver at search, right? SAT solvers have been tuned for decades to be extremely efficient at doing this sort of general purpose search with the learning, right? So, don't try to compete at a SAT solver with the thing it's best at. On the other hand, you could also try to recreate, write your own Fourier transform or something, but CASs and mathematical libraries have been developed over decades to do that effectively as well. So there's no sense in rolling your own if something's already available. You just have to put the SAT solver and CAS together, and you have something which is now, you have the great search power, but it's also much more expressive than just pure Boolean logic, which is downside of a SAT solver is it's very primitive in what you can express. So you kind of get the best of both worlds. And so I'm really excited about pushing this farther, right? I've been working on it several years, and I really think it's going to change forever what is considered feasible. And we're looking for these very specific mathematical objects. And I've seen it again and again, where you can come up with a SAT approach and search for something that runs okay. You come up with a CAS approach for something, and it also runs okay. But then when you put the two approaches together, you just get something which is running orders of magnitude faster than either of the individual approaches, right? You just have to get them together in just the right way, and it just kind of explodes. And I'm constantly surprised by how many different domains this kind of idea can be used in. There's a SC squared workshop being run annually for the last 6 years now, and they have many applications from like domains I would not have expected, like autonomous driving and economics. There's papers on using SAT plus CAS to search for circuits for matrix multiplication, and we've been using it to search for small Hawking spectral systems, which is used in the proof of the free will theorem from quantum physics. So even if you don't think, at first thought that SAT plus CAS could be used in your sort of problem, it's worthwhile, thinking about it a bit, maybe talking with some experts in SAT and CAS, and maybe seeing if you can come up with something, because if you can put these tools together, you can really get a huge, very good speed up. And so thanks everyone for listening to our talk, and we'd be happy to take any questions right now.
Thank you. Questions from the audience? There is a question in the chat from Linda Lee. Would you like to ask it, or should I read it?
I just wanted to add a comment to what Curtis just mentioned, which was that we are improving SAT solvers continually, and we are adding extra, more powerful proof systems to the solver. So traditional SAT solvers are only as powerful as a resolution proof system, but we are now exploring how we can extend it to an extended resolution proof system, which is a significantly more powerful proof system than just the resolution proof system. So just adding to that point.
Thanks. Let me first ask the question of Linda Lee, and then there's another hand raised. So the question is, what about CAS functionalities that do not have certificates? Does it mean that there is no certificate in those cases, or is there some way of still getting certificates?
Yeah, that's an issue, right? Because in general, CAS will not produce certificates. And so in that case, you have to basically just trust, either you find a CAS which will allow you to produce a certificate, or you just have to trust what the system's coming back with like you can trust the SAT part, but then you have to, trust what the computer algebra system is giving you.
Okay, thanks. Stanislav, question?
Hello. Okay, I have two questions. One simple technical and another more general. The technical is SAT instances for the projective plane of order 10. How large are they, right? In some moments we hear about systems handling millions of variables, yet you can put together thousands of clauses which nobody can bite, right? So what were the cases you had of 20, 30,000 hours? What were they dealing with?
So you can get this SAT instances exactly online. I can estimate it was in the thousands. So you have a Boolean variable for every entry in the matrix. We actually don't even need all the entries to show unsat. I think we use about half or maybe like a third of the entries. All of the entries would be 111 squared. So that's like 100,000.
Were you changing it to 3 SAT for better performance by humans, or you just fed very large clauses?
We did not enforce 3 SAT.
That could be beneficial quite often, there are
yes
cool ways to say things in the 3 SAT language which would break for longer clauses. Okay. And one more general, from my perspective, the SAT-based methods so far were not much used for Ramsey type problems. Well, they were here and there, but I'm not sure they worked that well. So did you try any SAT plus CAS approach to, say, decide cool instances of Ramsey arrowing problems?
That's future work. Yeah, we've been very interested in Ramsey, but we have not used SAPLCAS on it yet.
And we are happy to talk to anybody who's an expert in Ramsey theory to collaborate with us. We'll be very happy to learn from anybody who knows deeply about the subject, because that is definitely an area where we would like to explore. And I believe that will help us improve SAT technology much further, because the way SAT technology improves is by butting heads with really, really hard problems.
So there is a number of Ramsey instances of arrowing which are relatively small, yet as far as I know, the state-of-the-art solvers cannot do much to them, right?
Correct. Yeah, Ramsey is too difficult at the moment. It's too difficult.
How large is the certificate for the LAMPS problem?
Oh, yes. It was quite large. So the case 3 was the big one, and I believe it was like 100 terabytes.
Okay.
So.
As a kind of a practical question, to what extent is your system of math check a system that one can download and use, and to what extent is it more like a paradigm where you have to assemble the pieces yourself?
Yeah, at this stage, it's pretty much some assembly required. So everything's open source, so you can download it. But if you want to apply it to your own problem, yeah, you're going to need to, hook up the SAT solver to the computer algebra system yourself.
Okay, any more questions?
There's one question in the chat, I think.
All
Oh,
right.
yeah, thanks.
Thank you.
Sorry, it's not a question, it was just a comment.
Okay, if there are no more questions, well, let's thank Curtis and Vijay for an excellent talk.
Thank you.
This will be the last talk for November. Our next talk in this series will be December 1. And it will be Daniel Roberts speaking about theory of deep learning. So I look to see you all there. And, thanks again for attending.
Thanks. Bye-bye.
All right. Thank you.
Bye. Thank you so much. Thank you, Michael.
Sure. No problem. Well, I'll get back to you, sometime we can chat. Yeah. Very nice.